So the interest of studying these nice stuff we mentioned is our case for a condensed matter problem. So the Bloch band, the topology of the band, and the band structure. So let us remind ourselves with the Bloch wave function expression. So you have the self-periodic part, and this is the envelope part for the plane waves. And remember that the Hamiltonian evolution of or the energy dispersion relation for this such wave function can be characterized in a dispersion relation scalar feature. Okay, but now what we are going to see the geometric, the topological feature of the band structure, of the Bloch structure in a solid state problem. So let me tell you that one of the discoveries that made Dave Thouless justified for the Nobel Prize this year is that he discovered that if you look at this simple formula, it's said that n is equivalent to the line integral. So now we will take the integral. Let's consider you have a Berry flux or a Berry phase that you can have in a Brillouin zone, the decay momentum space of your solid state structure. So he said that if you take the integral of the vector potential, here our case is the Berry connection, you take the integral around the contour, line integral around this contour you want to trace. If you take around the Brillouin zone, and then you invoke again Stokes theorem, you take the integral around the Brillouin zone, the full edge of the Brillouin zone, as you can see here in this momentum space, it's actually equivalent. So around this area, you take the integral around, you take the integral of the Berry curvature around the whole area of the Brillouin zone. And he said that this is just an integer number. We call it the Chur number. He said this is an integer number. It can take 0, 1, 2, whatever. And also this Chur number, I would like to say that it's very featuring character of the topology of the band. So this is a magic, we call it a magic number. It's characteristic for the band, characteristic for the topological feature of the band. And it was studied first in electronic system, and we will see in a second that we can take it to the other scale, which is the non-electronic system. So now we have electrons in a lattice, the Brillouin zone, your solid state familiarity, the electrons in a lattice. But now we will see that we will generalize it to quantum matter, to quantum gases in optical lattices that we studied. So Dave Thouless also said that you can actually determine the number of edge channels of your problem using this Chur number, and if you take this formula and you see that the number of edge channel correspond to quantized whole conductance plateau. So this is what we call the quantized whole conductance. So this also, the whole conductance also quantized as the number of edge channels is also quantized. So this is what we call the bulk edge correspondence principle. The bulk edge correspondence principle for studying the relation between the edge channels, the number of integer number, Chur number, to the conductance plateau for xy for 2 dimensions. So let's take our interest for the quantum gases. So now we have our familiarity with cold atoms, and now we will see how to measure the phase shift that we saw in the last, just introducing the equations, this phase shift, the Berry phase that we say. So I would like to introduce to you now what we call the Aronoff-Bohm phase effect. So it's just simple. If you have 2 wave functions of 2 electrons, for example, and then you split it around the action of the existing magnetic field, and then the action of magnetic field affecting the 2 electrons or 2 clouds, 2 wave packets, and then you collect them back again, and you measure the phase shift that you saw, or that the electronic wave functions or electronic wave packets exhibit during their journey around this just splitting around. So if you remind yourself with what we said in the last video, if you take this is actually flux, magnetic flux, you take the contour integral around the curvature. Here does A, here A, the connection that we said, the Berry connection, but we will see here the Berry connection. Now it's just a vector potential. You trace you take the contour integral of the vector potential around the R space, which is nothing else than take the line integral of the area, just invoking Stokes theorem again of the curl of the vector potential around the area. And then you can recover what we call, this is what we call the Aronoff or Aron-Bohm phase structure. You take, this is the curl of the vector potential, the magnetic field around S, and this is corresponding to the flux and also per quantum flux per flux per quantum in your lattice, in your simple lattice. So this was a real space problem for Aronoff-Bohm phase. Now we have the momentum space. So now we consider a momentum space problem, and you have cold atoms. You have two wave packets for two atoms, cold atoms. You split them again, and then you collect them by the action of the Barry flux that you enclose inside. You can say the same, but here just change in parameter space R, and you take the contour integral again, and then you generalize it for the generalized curl of your Barry connection. You recover the Barry phase of flux, and this is just nothing else than the integral around the Barry connection for this area, which is called the Barry phase. Now you pick up a phase shift, and then you measure this phase shift. How you measure this phase shift quickly using cold atoms? We call our cold atom experiment with a simple lattice for the graphene. So let's consider this graphene. I will remind you with the graphene, you have the Dirac cones, the enclosed delta functions around the Dirac cones, and you have the dispersion relation for the graphene as Dirac cones, and if you remember, and you have the center of here is just a gamma point. So what we will do is that we will prepare the atoms in a coherent superposition state. Okay, this is one atom prepared in a coherent superposition state, and then we will expose it to a horizontal magnetic field. This is a horizontal magnetic field, and you will at the same time the horizontal magnetic field will have different effect on each spin, but the superposition state will also exhibit, and we will just apply a spin independent force in the horizontal and the vertical direction, and upon this you will see that this effects and this effect have different, and so you will see that the spin would go like this and the other spin will go like this around, and then you will apply what we learned in quantum optics and some of the videos, pi over 2 pulse to flip the spin again and to collect them for each pi over 2 pulse again here, and this way you would measure the phase shift that the coherent superposed atom actually exhibits during its journey here. This was nice that we have for each Dirac cone point, for each relativistic point in the graphene, you have the Barry flux localized at each. So let's say you have Barry flux here, and let's say you have Barry flux here. Let's say you have Barry flux here, Barry flux, Barry flux, Barry flux, actually localized in the Dirac cone relativistic points K and K prime. And by this way you can measure the phase shift that you pick, and this one of the graphs you can see here for the quasi-momentum, here the quasi-momentum, the crystal momentum, and here the phase that you pick. So let's sweep it, you get for 0. So once you just arrive at recovering one of the relativistic points of the K and K prime, you pick up a phase shift, and you can measure this phase shift. This is called a Dirac cone, and this Dirac cone is repetitive around, if you sweep it from 0 to whatever kind of crystal momentum you wish. So now it's a solid experiment that showed that you can measure this phase shift picking for cold atoms and recalling and just resembling the same of the Aronoff-Bohm phase interferometer that you can see for real space problem. Now and I will link you also to the paper that was very nice paper for this measurement technique, and this justifying what the Dave Thal is discovered for the Chern number, the quantized feature, and now you can measure upon this quantization the phase shift that you can see during the Barry physics problem. One remark to conclude with is the excitement that I'm exhibiting right now to see whom the Nobel Committee of the Royal Swedish Academy of Sciences would nominate their work for. And let's see how it works. So I hope that you liked the course, the set of videos. Feel free to feedback me, and thanks a lot for following.